All right, chemistry folks, we're gonna finish out this unit by going over polarity. Polarity. All right, so types of bonds. Let's just recap. Ionic bonds, you have a transfer of electrons from one atom to another, creates that positive ion and that negative ion, and that electrostatic force of attraction is the ionic bond. Then you have a covalent bond, which is a sharing of electrons between atoms. Instead of that transfer, which forms that electrostatic attraction, you have the sharing of electrons to get to an octet, which is a covalent bond. Now, beyond that, we actually have two types of covalent bonds. We have a nonpolar covalent bond, which means that there is an equal sharing of electrons. All right, they're shared equally, meaning they're not closer to one atom or the other. They're shared equally in between them. And then a polar covalent bond. There's an unequal sharing of electrons, and the electrons are going to be closer to one atom than they will be to the other. Now, what atom are they closer to? Going back to the property of electronegativity, electronegativity is the ability of an atom to attract an electron. So the electrons are going to be closer to the most electronegative atom. All right, so again, electronegativity is the ability of an atom to attract electrons in a chemical bond. And you get these polar bonds when you have a highly electronegative atom bonds to a much less electronegative atom. Now, I do want to mention here, it's kind of like a continuum. So you have a 100%, you can have a 100% nonpolar covalent, and then somewhere in between you have a polar covalent, and then eventually you get to a point where there's such an unequal sharing that it's more of an ionic bond, that transfer, and so then you have an ionic bond. So it's kind of a continuum here, if you will, if you think about it like that. Whereas you can have a 100% nonpolar covalent bond, and then somewhere between an ionic bond and that will be your polar covalent, and then eventually, if there's such an unequal sharing or such a large difference in electronegativity, you're going to have an ionic bond. All right, so how do we determine polarity? There's three ways. You can look at the difference in electronegativity. This is a very finite method, and in addition to that, you need to be given the electronegativity values, okay? They're not clearly given on any periodic table. You know the trend, but you need an actual value for these. So unless you're given that value, you're not going to be able to use this method. This is actually the method that we are not going to use. And here we'll still talk about electronegativity as a property and try to understand more about the polarity of certain bonds and molecules by knowing the general trend in electronegativity, but we're not going to be given an actual chart of electronegativity values. So we're really not going to use this first way. We are going to use the second way, types of atoms. This is another finite method, but you can use the tool that you'll always have, the periodic table, okay? And then lastly, the properties, looking at properties is the best way, because really and truly, knowing what the properties are, that's how you describe polar substances through their properties, and a nonpolar substance through their properties, and an ionic compound through their properties. So this is the best way. And so we're really going to use number two, but we're also going to go into talking about the properties, and in higher level chemistry courses, you could use a mixture of these methods to describe the polarity of a substance. All right, so determining polarity difference in electronegativity. A covalent bond is polar if there is a significant difference between the electronegativities of the two atoms. So for example, if the difference is between 0 and 0.4, that's going to be a non-polar covalent bond, okay? If the difference is between 0.4 and 1.8, polar covalent. And if it's above 1.8, ionic. Now, if you go and Google this and look at what other things are telling you, you might have slightly different values here for these ranges, but this is approximately what most of the ones that I saw earlier give, okay? Like I said, we're not really going to be using this, so didn't really care if it was the exact ones that most teachers use, but this is about right. All right. Determining the polarity. So let me just back up here. So because it's a difference in electronegativity, that's why you're going to need to be given the electronegativity values of these these atoms. Now keep in mind, electronegativity only goes up to 4 here. So if you think about that, it makes a little more sense. 0 to 0.4, then 0.4 to 1.8, and then 1.8 to, or anything greater than 1.8 all the way up to 4 would be ionic. All right, and secondly, types of atoms. A covalent bond is polar if there are two nonmetal atoms of different elements bonded. I actually misspelled metalloid staircase there. Metalloid staircase acts as the boundary between metals and nonmetals. So we're going to say if it's to the left of the metalloid staircase, it's a metal. If it's to the right, it's a nonmetal. Rarely will we ask you about the metalloids bonded to things, but just for the sake of this particular situation here, we're going to use the metalloid staircase as a finite boundary. All right, so if you have two of the same nonmetal atoms, for example, 2 chlorines or 2 carbons or 2 seleniums, that's going to be a nonpolar covalent bond. If you have 2 different nonmetal atoms, carbon and sulfur, carbon and chlorine, chlorine and sulfur, phosphorus and sulfur, oxygen and fluorine, that's going to be polar covalent. And if you have one metal and one nonmetal, such as Na and F, or rubidium and bromine, or yttrium and carbon, that's going to be ionic. So if we're just looking at the properties for substances, we can also speak to their polarities as well. All right, and so for example, if you have really low melting points and boiling points, you're going to have weak forces of attraction. This is representative of nonpolar covalent bonds that exist in that molecule. If they're higher melting points and boiling points, a little bit stronger than with the nonpolar that we saw, a little bit stronger forces, then you can say that it's a polar covalent. And then lastly, very high melting points and boiling points, very strong forces, these are going to be ionic. Like I said, typically we're going to use the second method where we just look at the periodic table and determine what types of atoms are there, and not worry about these others. And we'll talk about the properties in general of these different types of substances that contain these bonds, but won't really use this as the method for determining what kind of polarity they have or what kind of bonds are present. All right. So just looking at this here, let me fix this real quick. So I got, I just have to get it out of the way. So right here we have polar covalent bonds and dipoles. So when you're looking at these, sorry, I'm still working here. When you're looking at these substances here, so here we have carbon and fluorine. We know that there's a difference in electronegativity, and so you're going to have a dipole. Now, this little symbol that you see here, this is the lowercase Greek letter delta. All right, so putting that with a negative sign over the fluorine or anywhere around near the fluorine acknowledges that, hey, this is my more electronegative atom. This is going to be the negative end of this molecule. Doing the same thing but with a positive lets you know that that's going to be the positive end. All right, so again here we have electronegativity of 2.5 and 4. So we can see that there is going to be this difference in electronegativity, which is going to create a fairly polar bond. So yeah, everything I just said there. You can think about it as, since fluorine is more electronegative, those electrons are going to be spending more time around fluorine than carbon. So we say that a polar bond has a dipole. Now, to be clear, a dipole is actually a numerical value that gives us an idea of the magnitude of a bond or a molecule. We are not going to dive into a dipole moments and things like that. That is numerically, we would just simply say, oh, since this is a polar bond, this has a dipole. This has a dipole moment, which is just acknowledging that there are two poles, one positive and one negative. All right, so there's a difference in charge across that bond or that molecule. That's all that's talking about. So here we can see a nonpolar bond in HH and a polar bond in HCl. We'll see this even distribution of electrons right here, the electron cloud evenly distributing those electrons. This is a nonpolar bond. There is no dipole. Whereas down here, we do have a dipole. We have this HCl molecule, and the Cl is more electronegative, so we're going to have the negative end over here and the positive end over here on the hydrogen. And because of this, there's actually another way we could show this as a dipole. We could put a little plus sign here, and we could draw an arrow towards the end that is more electronegative. So here we see that again in the HF molecule, just two different ways to show that you have a polar molecule or bond, using these delta symbols here with the plus or minus, or using this arrow. All right, so what I want you to do is I want you to pause for a minute. I want you to quickly determine the bond type in the following. All right, you have your choices here, polar, nonpolar, and ionic. And like I said before, you're just going to use the location of the elements on the periodic table. Let's pause your video, jot these down, and come back and I'll give you the answers. Pause the video. All right, so here are the answers. Polar. CH is polar, HCl is polar, NaF is ionic, bromine is nonpolar, SO is polar, NH is polar, HO is polar, KCl is ionic, CSF is ionic, and ClCl is nonpolar. All right, so this is just bonds, but what if we're talking about an entire molecule? What's going on with an entire molecule? So we have to actually look at all of the bonds surrounding all of the bonds that exist there and determine if they can cancel each other out. So if one end of a molecule is slightly positive than another end of the molecule, then it's going to be a polar molecule. So let's take our first example that we have here. Or well, let me just read through the bullet points and then I'll go back and we can look at our examples. So it depends on the shape of the molecule. Okay, so here we have two examples, CO2 and H2O. CO2 is going to be a non-polar molecule, and here's why. Even though each CO bond is polar, across the entire molecule, it's going to be non-polar. Okay, so another way to look at this. Let me just get my things out here. This is where I would jump on the board and start writing away. So another way to look at this, so that you got this CO2 molecule here. Remember, it's a double bond on each side. Okay. Put my lone pairs there on the oxygens. It doesn't really matter here. So even though each one of these bonds is polar, which I'm going to which I'm going to show using these arrows here, the bonds are on opposite ends of the molecule and are of the same magnitude because they're the same bond. For that reason, they're going to cancel each other out, and over the course of this entire molecule, it's going to be non-polar, all right, because these polar bonds cancel each other out, all right? Now you might be thinking to yourself, but look, Mr. Lambert, H2O also has polar bonds that cancel each other out. But this is not the correct structure for H2O. Well, okay, this is the correct Lewis structure for H2O, but this is not the best way to write this on a 2D piece of paper. A better way to write this molecule is going to be like this, because at this point you should know that the molecular shape of H2O is bent. And because of this, this is a better way to write it, like the two examples I have here. And so even though you have these polar bonds here and here, they are not on opposite sides of the water molecules, so they're not canceling each other out. And you're going to get a net dipole looking something like that. Okay, and so this is going to be a polar molecule. Okay. So, rules. I say that cautiously. Rules. Because we could have a situation where these rules don't hold up. And you will, but not in this class. That'll be in another class. AP Chemistry and any other higher level chemistry course you take. These rules I have in green here aren't going to hold up. So first you need two things. You need the Lewis structure, and then you need to determine their ABE designation from the chart that I gave you, and it's also in the video. Basically what that means is how many bonding domains are there and how many non-bonding domains are there. Okay. Now symmetrical molecules are going to be non-polar if the surrounding atoms are identical and there are no lone pairs of atoms on the central atom. Now, I will say that second bullet point is only true for the molecular geometries we do in here. Now, if you look at the molecular geometries, or if you look at electron domain geometries that go beyond 4 electron domains, the 5, which is the trigonal bipyramidal, and then 6, which is the octahedral, that second bullet point, it's not always going to be true. Okay, and so I say that only up to 4 electron domains are these. Is this in here? What we have in green right here, true? Okay, so if it has atoms that are all the same and there are no lone pairs on the central atom, then it's not going to have a dipole because those bonds are going to cancel each other out. The polarity of those bonds is going to cancel each other out, and the entire molecule will be will be nonpolar. Okay, so molecules that are linear, trigonal planar, tetrahedral with the same surrounding atoms are going to be nonpolar. Okay, that's molecular geometry. Now, when you start adding on lone pairs, that's when you come into situations where you're not gonna have things canceling each other out, like we saw with water. Like we saw with the water molecule. Right back here. So we got to remember we have lone pairs on the oxygen atom here, 2 lone pairs. Whereas over here with carbon doesn't have any lone pairs. And I should say the surrounding atoms are identical and there are no lone pairs on the central atom. There are no lone pairs on the central atom. All right, so let's look at some examples here. Here you have CH4. All the atoms surrounding the central atom are the same, and there are no lone pairs. This is going to be nonpolar. Exchange one of those for chlorine. You're going to have all the atoms are not the same surrounding it. It's going to create this disparity in canceling out those charges, and so this molecule is going to be polar. It actually gives you, interestingly enough, you can see this number right here. We're not really going to worry about it, but you can see this is the magnitude of the dipole. It's what we call the dipole moment. You can see how it changes as the situation changes. Again, just notice that there is a dipole moment, which for our purposes means it's polar. Okay. So exchange, now you have 2 chlorines and 2 hydrogens surrounding this carbon atom. This is still going to be polar because this thing is not going to cancel it out. So here's the interesting thing about this. So if we were to write the Lewis structure for this, if we're to draw the Lewis structure, I'm all over the place here. If we were to draw the Lewis structure for this, we would actually see something that looks like, I cannot find mine. Here we go. We have this, but we got to think 3D. Okay, you see in the picture here, if you look at this 3D, these down here in the bottom right, these hydrogens here are going to be on one side of the molecule and the chlorines are going to be on the other side. And so this is actually an incorrect, or well, I shouldn't say incorrect. It's not the best way to draw the Lewis structure for CH2Cl2. A better way would be to draw it, and you do not have to do this. A better way would be to draw it like this. And I'm ignoring chlorine here, has lone pairs around it, sure. All right. This is coming out of the board, and then you have one where it's going into the board. All right, or this is used a lot in organic chemistry, but that would be a better way to write this on a 2D piece of paper. Again, not requiring you to. This one is perfectly fine. Okay, I'm just showing you another way that you may see if you're looking at some things online. And then again, we have 3 chlorines over here with 3 chlorines over here with 1 hydrogen, still going to be polar. And then if we have all chlorine surrounding, it becomes non-polar, just like CH4. Okay. Down here we have boron trifluoride. Remember, boron is happy with just 6 electrons, and so you have each one of these. Hate that. You have each one of these bonds that's polar, but they're in opposite directions, so they're going to cancel each other out. over the course of this whole molecule, so boron trifluoride will be non-polar. So you can certainly do this for these 9, and we can talk about them in class, but I also want you to go and determine the polarity of the molecules that's in assignment 4 of the worksheet that you had to draw those Lewis structures for this class. So determine the polarity, and you can just simply say it's NP or P. If you want to spell it out, that's fine. Hopefully this has been useful for you. Let me know if you have questions in class. Let your teacher know if you have questions in class, and have a great day.